So there comes a point in every presentation where it's time to brag. And even though it says achievements over there, really what it is just bragging. That's all we're going to really do for the next 5 minutes or so. So if anyone was here for the first couple of presentations that we had, the very first, we sort of made a promise. This promise was that we will achieve 10x. 10x, what I mean by 10x is that our implementation on the graphics card will be 10 times faster than the CPU. How we sort of reach this conclusion, various heuristics. But for now, I want to examine what 10x means. How fast is 10x? Is it a lot? Is 10x a lot? I mean, let's take a look at the varying cycles of computers over the years. How many times do you need to buy a new processor, and how fast is that processor? To answer that question, let's look at a very famous law, though it has a lot of criticism, we'll just use it as a base case for this. Moore's law basically states that the number of transistors over the years will double every year. Now we can sort of make a conclusion, though not completely accurate, that the CPU power, the CPU clock speed, will quadruple over every 3 years. Here's a nice little graph indicating, how this will occur, or how this has occurred over the past years. So let's see. So 10x, if we think about it, we'll get a new CPU every 4 years, and that'll be 4 times as faster. How many years will we need to wait for us to achieve 10x? Well, the answer is 7.5 years. Well, it's quite a lot. It's quite a lot of time to wait. It's also worth noting that Moore's law applies to the GPU as well. GPU has transistors as well, and they double over the years as well. So GPUs will always be faster than CPUs. They'll also, every time CPU increases, GPU is right ahead of it. So this, well, just to bring you back for a second, we said we would get 10x, I mean, we made this promise, but did we come through with it? Sadly, we didn't. We didn't live up to our standards. But I think we did okay. I think you'll be proud that we achieved 50x. If you direct your attention. I'm as shocked as you are, really. Here is our implementation. Here's a CPU implementation. This purple line over here is what we promised you. And the yellow line represents previous versions that we worked on. And we optimized it to get our nice little red line over here, which is approximately 50 times faster than the CPU implementation. If you guys want to go back to Moore's law, you can compute how many years you would wait. But I don't think that's necessary. I think you can imagine what speed will attain. This is just a graph representing our implementation over here and what we promised you as well, just to give you a better scale of things. Now, let's talk about how fast our algorithm is in comparison to other things. Well, we know it's 50 times faster than the CPU because, I've kind of pushed that on you guys a little bit. But it's also 4.3 times faster than our previous implementation. So we did some optimizations. I'll discuss that briefly. And we got 4.3 times faster than our previous implementation, which was like roughly 5 times faster than the CPU, or something like that, 10 times faster. And we promised you 10. So I think we lived up to our promise over there. Now, we also did something else. It's not just the CPU that we performed, that we enhanced. We also enhanced the memory. We enhanced the memory from a quadratic, now I'll explain this later, a quadratic to linear. What this means basically is, if I have a sequence inside my memory that would normally take up 2.5 gigabytes, it would take up 50 megabytes now. We use this technique to basically perform more processes, more threads, and this makes our algorithm overall a lot faster, which was major the reason why we had such a high improvement. So, and largely it contributed to the speed up. Now, we have another algorithm. Before, what I was talking about was the Smith-Waterman. And our DNA assembler, which I should note doesn't really have any parallel implementations. I think ours, there's strong reason to believe that ours is the only GPU implementation on CUDA. And we achieved 15x. It's pretty good too, Not, as you can see here, here's our nice little implementation on the GPU, and here's our implementation on the CPU. So what does this mean? We have faster algorithms, we know that, and we know that to a pretty good extent, but what does this mean for the biologists? What does this mean for the bioinformaticians? Well, it means that they can generate faster genetic research. It means that the discovery of relationships between species or organisms will be faster. It means that clinical advances in medicine and diagnostics. And it also means that your doctor will be able to prescribe a more efficient, more effective drug for you. All right, and I think we'll give it back to Mai for a little bit, and she'll take us home.